Hello, so welcome to this session on SystemVerilog Procedural Programming. So procedural programming is something that we have been seeing since Verilog. There's nothing it's not fundamentally new to SystemVerilog. The concepts that are fundamentally new to SystemVerilog are like the object-oriented programming, which didn't exist in the Verilog, or the declarative programming that we have seen in building assertions or the constraints. So those are the new programming paradigms that are introduced in the system Verilog, but procedural programming is something that has been there in the Verilog. So this session is going to be a refresher to some of those concepts, plus the procedural programming from Verilog has been enhanced in system Verilog. So we will look at some of the enhancements that have been done and how those are going to be useful. So before we proceed to the agenda of this session, let's just define the procedural programming. So procedural programming is based on concept of a procedure call. Okay, procedure is nothing but your like a subroutine, or basically simply a series of computational steps to be carried out, right, one after another. You exactly tell how it needs to be done, whereas in declarative programming you just tell at a very high level what needs to happen, but the exact steps in which it needs to do it is taken care by the simulator. Okay, and in the object oriented programming, the way you organize information, the inheritance, the polymorphism, the reuse, those are the those concepts are again very different. There is again some level of procedural programming involved, but it builds on the top of that. That's an additional layer. Whereas procedural programming is just your low layer, where you specify series of steps and they get executed, right? So that is your procedural programming. So let's go to the agenda of today's session. Okay, so this is the agenda for the today's session. We will be this has been divided it into two blocks. So we have procedural programming and then procedural blocks. Okay, and all the aspects that we discuss about the procedural programming are put in the procedural blocks. Okay, so that's the main division. Like for example, the code that we write has to be finally starting the execution in the form of an initial, final, right? So these are the blocks. These are the procedural blocks, are the constructs that give life to your procedural programming statements, right? Let's put it that way. So in the procedural programming, what we will look at is we will understand what are the some of the procedural programming statements, that is your if, case, looping, those constructs. We will understand them, and then we will revisit the tasks and functions, and then we will look at the assignment statements once again. The blocking, non-blocking, those assignment statements we'll revisit and look at it slightly more deeper. And then procedural timing control, the timing control that happens as a part of your assignments, we'll look at that. And then the one of the important topics is process. Then how do we have been doing some of the process as a part of the FIFO test bench as well, so we'll look now more formally and deeper into it. Then process control, how can we do it, and then how to do the inter-process communication. So these are the topics that we will cover in the procedural programming. And in terms of procedural blocks, the ones that really give the life to this procedural programming statements, we will cover initial, final blocks, the flavors of always block, then our sequential, or also called as begin end, and then the parallel blocks, which are nothing but fork and join. So we will cover those in the part of the procedural blocks. Okay, so we will start off with the procedural programming statements, and as a part of that, this is the overall scope that we look to cover. First is your simple condition if else statements. There are few additions in system Verilog, like there is a unique if, unique zero if, and priority if, but these are, I mean, like these are something that mostly not very useful from verification perspective. So we are not really going to cover this, but they are present in LRM. So if you are interested, you can refer to it. They are mostly useful in design. So then we will cover the case statements that are useful in modeling FSMs. And then again, there are few more different types of case statements, like you have unique case 0, unique 0 case, priority case, and then there is a case X and case Z. We will not be covering these. Again, these are part of LRM. You can refer if you are interested. And then we will be covering the all types of looping statements. There are some new constructs that have been introduced in SystemVerilog. We'll look at it. And then we'll look at the jump statements, which are very helpful to either continue or break from the loop. So we will be looking at those. So let's jump into the if. So if statement, I think we are mostly familiar. So I have put in some code snippet. So the way if works is if you look at some condition, and then if there are multiple statements, then you will have to put a begin end. If it is a single statement, then you don't need to put the begin end. And if this condition is true, then these begin end statements will get executed that follow the if statement. Then else will come if this particular condition is false. If it is a single statement, you don't need a begin end block, but if it's multiple statements, you need a begin end block. And within the begin end block, again, you can put any procedural coding statement that will execute if this expression is false. There is also like a priority type of a structure that you can create with if and else if. So here this was only one condition, that is either true or false, but if you have multiple conditions, then you can essentially you can use this else if type of a structure. If particular expression begin end, and then you can write your procedural code over here. And then of course here I think we don't really need this begin end, it's there just for the sake of completeness. So then you have again else, and then you have if. You can check another condition begin end. You can do series of this, and towards the end else, this is a default. So if none of these upper conditions get satisfied, then this final else will get executed. And these if series of if else if will execute in the order that you have specified. That is, let's say if the third if is true, then it will first execute if, check that it is false, it will come to this else if, then it will check if this is false, and then it will execute this if. And once this if is satisfied, this whole if structure is completed, and the control follows the next statement after this block. So this is how the the conditional decision statement is structured in SystemVerilog. And you can do multiple levels of nesting of both the if else and if else if. You can do any level of nesting you can do. So that's about if statement. Then you have the case statements, very simple. So multi-way branching. So if say case sig, and then let's say if it is one tick bz, then you execute some series of statements. If it's one tick bz x, you are executing some series of statements. And if none of the conditions are satisfied, are specified or satisfied, then you can put a default statement which will execute if none of these expressions are true. Similarly, I think the case statement is very useful in implementing the finite state machines. FSMs are not just implemented in the design, FSMs are also implemented in the verification components. But we don't worry about the synthesizability of the state machines, but state machines are implemented in the verification components, especially the BFMs. Use the bus functional models do use a lot of FSMs to build the protocol state machines that are specified in the requirements. So you can build a state machine case FSM state, and then the name of the state, then again begin end. You do a series of the operations that you want. Of course, the case that I'm showing over here is actually a synthesizable one. You can see the non-blocking statements, but nonetheless the structure will remain same. But the operations that you perform within each of these states is going to be something that's going to be different in the case of verification. So you might be calling series of function and task calls for each of the state, and then you will set up the next state, which when you execute the loop for the next time, it will execute it with the updated state. But from the case point of view, you say case, the variable name, and this variable could be enum as well. So here it's actually a enum type of a variable. Then you can specify, so this condition can be expression as well, so you can use the expressions, and multiple values can be specified by a comma separated list, and you can put a begin end block. So that way the case statement helps you do multi-way branching. I think you just, the other thing that you have to remember is this default, which is used if none of these conditions are satisfied. Then you tend to use the default statement. So that's about the case statement. Okay, loops. So you have bunch of, I think, like to be 7 to be precise, so 7 different ways in which you can do the looping in the SystemVerilog. So you have your simple for loop, C type of a for loop. So you can say for int of I equal to 0. So you don't have to declare the index variable separately, so you can just do it as a part of your loop itself. And then you can do an incrementing loop where you keep incrementing the index. You start off from the initial value, which could be 0, but basically less than your end condition, and then you keep incrementing the index and do the loop. Of course, you need to put the begin and end over here. I have not shown that. If it is a single statement, you don't need the begin and end, but if it is a multiple statements that you're executing as a part of your loop, you need to put the begin and end. And then you can have a decrementing index where the initial value starts off with a higher value and keeps decrementing till to some lower value, or typically to a 0, and then you loop through it. And as a one thing that you can do is, as a part of your, so this type of a C type of a for loop actually consists of 3 components over here. You have initialization, you have condition checking, and then the update, right? So these are the 3 different parts. And in the initialization part, you can actually initialize multiple variables. If you want, you can initialize some local variables as well that you intend to use inside the loop. So it's initializing index variable and some additional variable, and those can be a comma separated list. You can do that way. And towards where you apply the you update the index condition, there also you can put a comma and do the multiple updates. So this is allowed for the for loops. The second one is the for each loop. So for each loop is very helpful when you iterate through like queues especially, or even the dynamic arrays. So one dimensional arrays, this for each of the array name, and in the square brackets you put the index I. This character can be anything. Here I use the variable name I, but can be any name can be used. And inside that for each loop, now when you say this particular variable name, for example here APB protocol of CG of I, so I'm actually here, there is a queue of cover groups that have been specified, and each of them are being instanced. So you can have a queue of classes, and you can do this way and instance them. So when I say APB protocol CG of I, it gives access to this particular value inside the array, but you can also use the value of I as an index. So both are available inside the for each loop. So it is very handy. You don't need to know how many elements are present in the queue or in the dynamic array. Using the for each, you can just loop through them, or you can iterate through them. So so that way it is very helpful. You can also go loop through using the for each. You can loop through the multi-dimensional array. So this is the unpacked array, because as you can see, the dimensions are specified on the right hand side of your array name. So it's an unpacked array. So you say for each, and then in a single square bracket you put whatever the dimensions, one variable name per dimension. So here in the comma separated list, so I comma j comma k, each of them representing one of the dimensions, and then you can loop through that, and it will go through all the elements as if it's a 3 nested loops, right? So equivalent to that, it will go through all the elements, and you can do the processing. And of course we have been using the forever loop for a lot of things already. We have seen this in the FIFO test bench as well. Forever is the loop that we use in all active components. Even the simple clock generation, you use the forever. As the name suggests, it will keep executing forever. There's no condition to break unless you exit it in some way. Either you use the jump statements, or when the simulation terminates, it will come out. And then you have the while loop. So while, and then as long as the condition is true, it will keep executing the loop, and when the condition becomes false, the control will come to the next statement after the while loop. So you have the while, and you also have a do while. So the way, I mean, this one we have used it in the FIFO test bench. In fact, that's the code snippet that I have put it over here. So it's the difference between while and the do while is that the do while will execute the statements present within this begin and end at least once, right? Whereas in case of while, what can happen is that if this particular condition is false, then it won't execute the content of the loop even once, right? But whereas do while, it will execute at least once, and then it will check for the condition, and if the condition is true, it will continue executing the do while loop, and if the condition is false, it will come out of the do while loop. Okay, so whenever you have the requirement that you want to execute at least once and then check the condition, then you should be using the do while loop. Okay, so then you have a repeat. So repeat is another type of a loop. The good thing about repeat is that you don't even really need an index variable. So sometimes this is very handy. Of course, you might have to keep an extra count type of a variable if you need to debug the repeat to figure out how many times it has looped through, but it's very handy. So you say repeat, and you give a either it could be an expression or a constant number, and then begin end, and this will loop through the number of times that it has been specified. So depending on the type of application, so supposing if you don't have any usage for the index variable, then and it's quick one, you can do the repeat. For the queues and the dynamic arrays, especially the one-dimensional ones, which we tend to use very frequently, your for each is very useful. Forever, of course, as we have seen in every active component, we do use forever. And classic for loop, yeah, I think that is we have seen enough of those. I don't need to tell you. Between while and do while, just remember that if you need to do one more iteration, then you use at least one iteration, then you use do while, and whereas while just checks while entering itself. So depending on the type of requirement that you have, you can choose one of these 7 looping constructs. So each one of them, each one of them is useful for different scenarios. There are 3 types of jump statements that are supported. So those are like continue, break, and then the return. Okay, so let's look at each of the the use cases for each of the jump statements. So when and this continue and break are mainly they can only be used inside the loop. And what happens is when you when you are doing the looping, if on a meeting certain condition, if you want to exit it right at that particular point, right, so then you can use the break. So break statement will jump out of the loop. So here, for example, we are getting all the components, and then it returns. We have a comps of this is the queue, and then we are using the for each to go through each of the item, and if that item name matches with some component name, then we want to break, because we have found that and we want to do something with it. Okay, so as soon as you are looping through something, and as soon as certain criteria is met, you want to come out of the loop to use that element and do some further processing, then you use the break statement. And the way continue works is that as like there could be, if you while you are doing the looping and you want to skip processing for certain expressions or certain values, then you can use continue. So what the continue does is, as soon as the continue is encountered, the processing will go back to this looping construct, and it will update the condition, and it will reevaluate whether it is meeting still the conditional check, and if it is meeting, then it will come into it. For example, in this case, we are looping from 0 to 8, and then if the value of index is greater than 2 and less than 7, we are saying continue. So which means that when the value becomes equal to 3, right, it will go back and it won't display that particular number in this case, right? But maybe in your real life usage, you might have some processing over here, that is something that you can skip, and you can go further with the next value processing. So it will come back and it will do the increment to the value of 4, and it will check that 4 is less than 8 and come back and re-execute the loop. So that will also get skipped. So till the value 6, it will get skipped, so those won't get printed, okay, because this display statement will not execute. So and there is one special case. So what happens is, we'll see some of these examples in the next few slides as well, that if I am putting a for loop outside, and then say instead of this if over here, if I had a fork, okay, so when you want to launch multiple threads, we will see one such example. When you want to launch multiple threads, you can do that. So you can put a for, and then you can put a fork over here and keep launching multiple threads. So if you do that, then what that means is that you cannot use continue and break statement inside that fork join, because once you have done the fork, the context has moved on to the thread. So this for loop is no longer applicable to the thread that has already been launched. In fact, the thread that has been launched will not even be aware of this for loop, and we will see that it can't even see this index value. In fact, right, if you want to see this index value, then you have to declare one automatic variable inside this block, copy to that, and then pass it to that particular process if at all you want to see the index. So the point is, the continue and break are applicable in the context of loop, and if at all you do fork inside the loop, then the thread that has been launched will not be aware of this for loop. So you cannot use continue and break inside that thread and expect that to take effect on this particular loop. Okay, so that won't happen. The return statement can only be used in subroutine. Okay, in function, you can return a value, and the return statement can have an expression which matches the correct type that you have specified. So if you have said function int, then when you are returning, it should be of the integer type. That's what it means. So these are the three jump statements that are available in the SystemVerilog. So we have completed the procedural programming statements, and we will look. So the subroutines are another important part of the procedural programming in general. So we had looked at procedural programming statements, and this is part of the subroutines are another part of the procedural programming. So in the context of subroutines, we'll look into tasks and functions. What are the differences? Then, like, how does a static task, like how does a task or function with static lifetime behave, and how does a task or functions and the variables within them with the automatic lifetime behave. We will look into it. And then how is the difference between, so when we pass arguments to tasks or functions, when we pass by value, which is a default mechanism, how is this different from pass by reference? We will look into it. And then we'll close this one with the parameterized tasks and functions. See, the parameterization is one thing, that you can parameterize modules, and you can parameterize interfaces, you can parameterize classes. So unless and until the functions and procedures within those constructs also support parameterization, the overall parameterization won't be successful. So we'll briefly look into how the tasks and functions themselves support the parameterization. Okay, we'll start with tasks. So in the context of task, what we need to understand is that, yeah, every task will have this task and end task, and then it will have a name, and then it will have a set of arguments, right? And then we need to call the particular task, or we also call it as formally enabling the task. We need to call it to invoke the statements present within the task, and then there's a concept of lifetime. So these are the key aspects associated with the task. So what is the name of the task? What are the arguments list that we are passing? Then how do we call that particular task? And then what is the lifetime of a task? These are the concepts that we need to understand. And as we all already know, the tasks can have delays, they can consume time, and then tasks can call other tasks and functions, because a task can call other tasks, because as we know, the task can have delays, so only task can call task. The functions cannot call tasks because functions cannot have delays, right? That is a point. And then the tasks can take a formal argument list, and this argument list can be defined in two ways. Typically we have used it in this format, so we say task, name of the task, and in the parenthesis we specify the direction, data type, and the name of the argument that we intend to pass. But there is another format that is also supported. It looks something like this. So you say task my task 2, and it ends with the semicolon at that point, and then later you define the direction of the variables, and then the data type of variables. So this is another way of defining tasks, although I have myself have been using the format one for most of my work. But these two different types that are supported, so let's say that if there is an existing code base and you see something like this, then you should not feel oh, what is this? This is something new. No. So this is another format that is supported. Then the default data type for formal arguments in SystemVerilog is logic. Okay, we have already studied about the logic data type. It's a variable and can take 4 values. And then the default direction of the arguments is input, and default type, unless specified, it can also be inferred from previous arguments. Okay, so that is like once I define one argument and the subsequent arguments, if I don't specify the type over here, then it will take it from the previous arguments type. And task ends when it encounters an end task, or you can also add a return. You can't return a value, but you can just add a like a return and semicolon without any value, and that will exit the task context, right? And so what happens is, as we called out, when you call a particular task, the input formal arguments, the value gets copied at the beginning. So when you call a particular task, the value that you are passing as a part of your call gets copied at the beginning inside the task, and the output type of your formal arguments, the whatever the processing you do, it gets copied at the end. And then for the in-out, what happens is the value gets copied at the beginning and then at the end into the same variable. Why we are emphasizing this fact as to when it gets copied is because if there are any changes in the intermediate stage, then even if I have an output, like if I'm modifying some values for that particular output argument in the middle of the task execution. So what do I mean by that is a task can consume time, right? So I'm consuming time, so and I'm modifying, so that won't be visible to the context outside the task, because we can have multiple threads running. Okay, so a thread that is calling the task could have forked off the task, and then this particular task has delays and it's modifying the output. That won't be visible to the task calling or to the at the other places. But if I am passing it by reference, then the value changes will be visible even during the execution. So to emphasize the fact that when you pass by reference, any value changes will be visible. If I am passing it as an input, then any changes that are happening parallelly in the other thread will be visible to this task. Or if I am passing it as an output, and if the task is changing it, it will be visible. And of course in out, then both the ways it will be visible. So that difference we wanted to emphasize by this fact that it gets copied only at the beginning and end. So with that point, I wanted to emphasize that when you pass it by reference, the value changes will be visible, but when you pass it by value, then the copy happens only either at the beginning or end and not in the intermediate stages. Okay, let's understand this static versus automatic. This is a very important concept to understand. So tasks defined within a module, interface, program or package, they tend to default to static. They by default they tend to be static, and whereas if you define it inside the class, they are automatic by default. Okay, so first understand this point. We will look little deeper into what does this static and automatic mean with some examples, but first this fact you keep it in mind. The class it's automatic and rest of the constructs it is static by default. And the ones that are static, what happens is they will have no call stack either for arguments or variables local to the routine. So we saw that we can pass formal arguments to the task, and inside the task also we can declare local variables that we can use while we implement the algorithm inside the task, right? When we have a static lifetime, right, there is no stack. Generally what happens is you guys are aware of the basic concept of stack. So that is whenever a subroutine is called, it is pushed, the arguments when they are passed by value, they are pushed onto the stack, and any local variable are again created on the stack. So this is the fundamental programming concept. It even exists at the assembly level, if you guys remember. So when we create it as a static, then it's not allocated on the stack. Whatever gets allocated on the stack is dynamic, but for the static there is no allocation of the formal arguments or the internal variables on the stack. So once it is declared as static, then the either the arguments or any the local variables, they are just allocated statically, and they are shared among the multiple instances of the task that can be running. So this parallelism is an important concept. If it's not clear, then this is going to be hard to understand. So you have to understand that I can fork, like I can put a for loop, I can fork, and inside that I could be calling a task multiple times, right? So if I do that, the arguments in a static task, there's a common set of arguments that gets used, and even the variables that I have declared local variables, there's a common copy that gets used across the multiple instances of tasks that I'm calling. And the functions are also static, and the functions we cannot use in the recursion if it is a static type of a function, because by default for the recursion to work, what happens is a function calls itself and then it keeps returning the values. Those returned values have to be stored on a stack, and then you pull them out and do some operation and give out the final value. So since there is no stack on which the either the arguments or the local variables within the tasks and functions are allocated, you cannot use static function for recursions. So this is a point that you have to remember. No recursion with static functions. Okay, and then the static task, this is one other point, that if I have multiple instances of a single module, then each of the module will have a separate storage, right? So but within that module, when you have multiple threads of the same tasks are running, then they will share the common storage. Okay, but whereas if you compare it with the class, even if you have a static variable inside a class, even when you create multiple instances of classes, they share a common variable. Okay, this is a fine point that you need to remember, that if inside the module, even when you create the multiple instances of the module, each one of them will have a separate static storage, whereas the classes will share a common static storage. And from the Verilog 2001 onwards, there is this concept of automatic lifetime qualifier that has been provided for the functions and the tasks. And the main intent is that in general, in any procedural programming languages, by default functions are automatic. That is, all their arguments, arguments or the local variables within the functions, they all get allocated on the stack, and hence they support recursion. So that is the normal behavior which is expected. So from Verilog 2001 onwards, even the with the concept of automatic qualifier, the functions can be like equivalent to your C programming function, and they can be used for recursion, provided you use the automatic qualifier for the functions, or they are functions present in the class which are automatic by default. So let's next little bit we'll look into a little bit more examples of how the static versus automatic difference manifests. Okay, so we have seen how the what is the default nature of static versus automatic. That we saw that by default in anything other than class, they are static. So if you want to explicitly control, right, so there's one is a default control, but if you want to explicitly control, then you can use this static or automatic lifetime qualifier keyword, and this keyword has to appear on the right side of your function or task keyword. So you say function, then you can say static or automatic, and the name of the return value and the name of the function and the set of input arguments that you are passing, or you can say task automatic or task static, and then name of your task and the set of arguments that you are passing. So we will see some examples that will make it more clear. Then tasks can be defined to use the automatic storage in the following ways. So one is, as we talked about, you can use the explicit automatic keyword, and of course this is optional as a part of your task or a function declaration. And then so there is one more thing, that your module or the interface or program, they can be made to exhibit an automatic behavior. So you can say module automatic and some name of your module. This is allowed in SystemVerilog. If you do this, then the tasks or functions declared in such module will be automatic by default. Okay, so if the construct itself, the container itself is made automatic, then whatever it contains will become automatic as well. Although the module by default is static, but if you make module automatic and the name of the module, then all the tasks and functions within this by default become automatic, although you are not saying task automatic. Okay, then task defined task, it applies to functions also. Task or functions defined within the class are automatic by default. I think this is something that we have called it out. And all the items, right, all the variables declared within the automatic task are allocated dynamically, right? So for each invocation they are allocated, and all the formal arguments and any local variables are also stored on the stack. So that way they can dynamically so each of the invocation can have its own copy. Okay, and all variables of automatic task shall be replicated on each concurrent task invocation to store those specific values. Okay, so this, I mean, both of these in some way mean the same thing, but this is an important point, that when it is automatic, both the arguments that we are using as well as the variables that we are declaring inside, they all get allocated on stack, and what that translates to us as users is that the concurrent invocation of the same task will have the their own independent set of values, right? That's what it translates. So I think once we look at an example, it will become more. So this static versus automatic, okay, let's look at it from two point of view. One is the variables, the local variables that we create within a block. It could be in task, or it could be in general in any begin end block context. And the second one, specifically from the tasks point of view, from the arguments that we are passing, how these two behave differently. Okay, the concept is same, but how do these two things behave differently? Let's look at it from the examples and understand. So when we say static, there are static versus automatic. There are two things that we need to understand, right? When does it get allocated and when does it get initialized? These are the two key points that you need to understand. So a static variable, it gets allocated as soon as your simulation starts, and it exists for your whole simulation. Whereas automatic variable gets allocated only when we enter that particular task or a block. Okay, and as soon as that particular context gets completed, that either the block finishes its last statement or the task finishes its last statement, then the automatic variable that we had allocated gets deallocated. Okay, that is what happens with the automatic variable. And an automatic, so this is the from the point of view of its storage point of view or the lifetime point of view. But whereas from the initialization point of view, an automatic variable is initialized every time the task, function or the block containing it is entered. So as soon as it gets entered, it gets initialized. You might have an explicit initialization, in which case it gets initialized with whatever the explicit value that you are passing. And even if you don't have an explicit initialization, for every data type there is a default value. Like int, there will be 0. For a class object, it will be null. So there will be a default value. It will get initialized with that particular default value as soon as it enters the block. But it will get initialized either with explicit value or the implicit value, depending on the data type that you are using. So for the what happens for the static variable from the initialization point of view, since it's already exists and so it is already getting utilized, so it is not initialized. It's initialized only once when it was created. Generally the variables gets initialized only when they get created, not and or you are explicitly initializing. But so since the static variable already exists, it won't get initialized. Okay, so this is the difference from the point of view of lifetime of a static variable and the lifetime of the automatic variable, and as well as from the initialization point of view. So static variable gets allocated only during the beginning, exists throughout the simulation, initialized only once. Automatic variables gets allocated every time you enter the context of that block or task or function, and then gets initialized every time it gets dynamically created. Okay, so now these concepts, let's look at it from an example point of view to see whether it holds good. So in this program, what we have is we have one initial block, and in the at the context of initial begin end, the outside begin end, we have two count variables. So one is static int, and we are saying OS outside count, and then it's a static. Then we have automatic, it's outside count and it's of the type automatic. Both of them we have initialized it to 1. Okay, there is another begin and end block which is in the context of do while, and we are creating two more variables over here. So this is again one static variable which is inside is, which is inside, and one automatic variable which is again inside is, and both of them have been initialized to 1. So we essentially have 4 variables, and we have 2 blocks, and this block, outside block, gets executed only once because of this initial begin end, whereas the loop gets executed multiple times. So we have now variation. So let's observe what happens. So inside the loop, what we are doing, we are waiting for one ns, and then we are displaying the values of all 4 variables. We are incrementing all 4 variables by 1, and then we are saying if the $time is less than 10 ns, we keep looping. So it'll probably execute some 9 times, and we will be able to see what are the values, right? So I have now put the output displayed for some 3 iterations, but the same pattern will continue as well. So if you look at it, the OS count. So let's look at the first OS variables, right? So OS variables for both the static and automatic, if you look at it, in the first iteration they are displaying the value of 1, in the second iteration they are displaying the value of 2, and in the third iteration they are displaying the value of 3. So very predictable, because we are initializing them once, and thereon we are updating the values, and automatic was allocated over here and it remains allocated. The static also is allocated, automatic is also allocated. Since we are not re-entering this block and there is only one thread that is executing this particular block, it is getting updated with whatever the value that we are incrementing in the loop. But if we look at the internal variables, now this begin and end keeps executing again and again. If you see the static variable first, so first iteration it is 1, second iteration it has become 2, third iteration it has become 3. Why? Because static variable gets allocated only once and initialized only once, and thereon it won't change. Although you are re-entering the loop, this initialization is not getting executed because this variable already exists. Okay, this is a point that you have to note, that this already exists, so it is initialized only once, and thereon we are just incrementing and printing the value. Okay, so you see that the inside static variables don't get reinitialized again and again because it is already allocated. It just keeps incrementing. Now, whereas we look at the automatic variable, which is the last one over here, the first iteration value is 1, second iteration value is 1, third iteration value is 1, and it will be similar behavior for the subsequent iterations as well. So what's happening over here is every time we enter to the beginning of loop and enter this begin and end block, which is what is most important point. So when we enter this begin and end block, the automatic variable gets allocated again. Okay, and it is so it only exists till the end of this block. Once it is end, that particular variable gets deallocated and it comes back and it gets reallocated again. Okay, so it has gotten reallocated, and after reallocation it is getting initialized again, and hence it is showing the value of 1. It is not getting updated. So I hope this example clarifies. You should also you can take the same example and experiment to get the more clarity. Okay, in the previous slide, we looked at the static versus automatic difference from the variable point of view. Okay, so we had decided that we look at it from two point of view, right? One is from the variable point of view, and another is from the point of view of arguments passed to the task. So in this example, let's look at how the static versus automatic behave when we look at the from the arguments point of view. So on the left hand side I have this task add. Okay, and let's say that if this task is present as part of module, so it's a static task, and then I'm passing two parameters int a and b. Default direction will be input, and what we are doing is we are displaying the values of the arguments and the time at the beginning of task, and waiting for 2-unit delay, then again displaying the parameter values, then the time, and then we are doing some of these two variables as well. And then we have one initial block where we are forking two threads, right? So this begin end is one thread and this begin end is another thread, and we are calling the static task. So in the first begin and end I'm calling it with values 2 and 3, and second one I'm calling it with values 3 and 4. Note that it's called after 1-unit delay. Okay, so this is our setup. So now let's understand what's happening. So if you look at the output, I am saying, so here when this initial block executes, both of these will start in parallel. Okay, and the call to this add task will go and it will come here, and this task will consume this 2 units of time. Okay, and now so I have called it, and then it says 0 input a equal to 2 and b equal to 3. So that is the arguments that I have passed, and it has received it successfully. Okay, then this task is blocked because we have 2 units of delay over here, whereas in the second thread that we had launched was blocked for 1 unit of delay, and let's say after that 1 unit of delay it calls this add task again. Okay, now it's passing this values 3 and 4. So at time unit 1 we are seeing the input a equal to 3 and b is equal to 4. Now at 2, after the 2 time unit, this particular task has completed. The first time that I had called has completed. So at 2 it is going to say a equal to 3 and b equal to 4. Okay, so now what has happened? And they is saying sum equal to 7. And then the one that I had launched at time unit 1, that will complete with 2, 1 plus 2, it will complete at 3, and there also it is showing a equal to 3, b equal to 4, and sum is equal to 7. So both of them are showing the same value. So what does this mean? This means that this task, while it was in progress, we had allocated these two variables a and b. But since it's a static task, there is only one copy of these formal arguments a and b, and after one time unit, while this task was, the first one was still executing, the second invocation to the same task was made, and we passed the argument values 3 and 4, and now since we have only one copy of the formal arguments, they got overridden. Okay, so even the first invocation after the completion of 2, it was looking at the same copy, and hence the sum became 7. Okay, now the same example wherein what we have done, the change is now we have made it a task as automatic. Okay, we have added this automatic lifetime qualifier. Rest of the setup remains the same. And if we look at the output, of course the input, there is no surprise in both the cases. It was able to receive the inputs correctly, correct. But when we look at the output, right, this first invocation is showing 2 and 3, and it's showing it as 5, and the second invocation is 3 and 4, showing it as 7. Because of the automatic lifetime, every time we invoke the task, the formal arguments gets allocated on the stack. Okay, that is why the first invocation will have its own copy which will contain the value 2 and 3, and the second invocation will have its own copy which will contain the value 3 and 4, and hence we are able to see the sum as 5 and 7. So I hope this gives the clarity of how the static versus automatic behaves from both the individual variable point of view and from the point of view of the formal arguments. Okay, there are few more facts associated with this static versus automatic. Let's close on them. Automatic task items cannot be accessed by hierarchical references. Okay, so you cannot automatic tasks just exists during the lifetime, and so you cannot make like a hierarchical reference which are static in nature to the automatic task. So this is one point. And second point is the specific local variables can be declared as automatic within the static task and static within the automatic task. So what happens is that when you have an automatic task, by default all the local variables within that task will be automatic. So but if you want something to be static, you can explicitly declare them as static, that is possible, or vice versa, both of them are possible. Then because the variables declared in automatic tasks are deallocated at the end of the task, so they shall not be assigned value using the non-blocking assignments, because non-blocking assignments get scheduled, and what if the task has finished its lifetime? Now that becomes inconsistent behavior. That's why you cannot do non-blocking assignments to the automatic variable. So this is a subtle point that you need to keep it in mind. So just let's look at one simple example. So if I have a task automatic and I'm just saying, let's say create wave, and I'm passing some variables by reference. Okay, don't worry about the fact that it is by reference. I know that you don't fully understand the concept of reference at this point, but just understand the fact that we are passing the arguments, and this could have been an output argument as well. And since this is automatic, even the arguments are automatic in nature. So I can't use a non-blocking assignment over here. Okay. So if I do a non-blocking assignment to these variables, then the compiler itself will give the error saying that it is incorrect. Okay. So you have to do the blocking assignment. So this is the point. But whereas I have another task over here, this task, of course, this task was a part of a module, so by default it was static, so I had to make it automatic. But this is a task which is present part of a class, so you can see that it's a push DRV class, and then so it is automatic by default, and I am doing non-blocking assignments, right? So I am doing non-blocking assignment to the virtual interface that is present within the class. So now the point to note is that this virtual interface that we are talking about is not a part of this automatic task variable. So this is not going to exist only for the lifetime of this particular task. It's going to exist for the lifetime of the class, that the object of that class we are using. So to this interface we can still do the non-blocking assignment. So only to the local automatic variables you cannot do the non-blocking assignment. But if it is something non-local, since it's non-local, right, it's a part of the class property, not the member of the this particular task, so you can still do the non-blocking assignment. So this is some few points that you want to keep it in mind. So functions primary purpose is to return a value that is to be used in the expression, and similar to tasks, the functions can also be defined in these two formats, that you can say function, the return value, and then the name of the function, and then the arguments that you are passing, and then whatever the processing that you want to do. Typically you will have a return that's matching the type that you have specified, then the end function when it completes, or you can just say function, the return value type, and then the name of the function semicolon, and then you specify your input, and then the data type, or you can separate out even the direction and the data type as well. So both the type of declaration formats, as we had seen in even in the case of task, are applicable even to the function. And you, if the function doesn't return anything, then you can specify it as a void, and this is something that you can use, instead of task sometime, if it executes within the single time step. As we know, the tasks can consume time, but the function cannot contain any time control statements, which means that like a hash which is specifying some absolute delays, or double hash which we have seen from the clocking block in terms of the number of clocks, the default clock that we have specified, at you are waiting for an event at passage of clock, or at a named event, which we will see in the future. Fork join, we have briefly seen it. You launch multiple threads, and those threads could contain delays, and a join will make them wait for it, so you cannot use fork join. Fork join any also has to wait for at least one thread, and that thread can contain delay, so you cannot use it. Wait, level sensitive, you are waiting for a level sensitive value to be, like a particular expression to be satisfied. We had seen this even in the context of a FIFO test bench, wherein in the when we were generating the pop, for example, or where we were waiting for asynchronous reset. So in the pop generation, we were waiting for the count mismatch, so that only after the push is generated, we were waiting for the pop to be generated. Then you have wait order, and then you have expect, which we had seen in the context of assertions. So any of the statements that can consume time, you cannot use it in the function. And then functions of course cannot call tasks, because again the same rule, that the tasks can contain delay, so hence functions cannot call tasks. And in terms of the formal arguments, if you don't specify the direction, the default direction is input, and if you don't specify the data type, the default data type is logic. Okay, so function definition so whenever you declare a function, right? So we have the return value. So it internally creates one variable which is with the name of the function, and then the variable type will be whatever the type that you have declared. Okay, so you can actually assign that particular variable with the value, okay, and that is the value that it will return, or you can do an explicit return. Both are possible, but there every function internally contains a variable with the name of that function with the data type matching the return value. And then functions can also be static or automatic, and the rules that we have discussed for the variables within the begin end and the formal arguments in the context of task apply to function as well. And the non-blocking assignments, you can make non-blocking assignments, they don't consume any time, whereas blocking assignments consume time. So you can use non-blocking assignments within the function. We will be seeing named events. So named event trigger doesn't consume any time, so named event trigger can be done. You cannot wait on a named event, but you can trigger the named event from the function. Clocking block drives, so this is one of the items. So like we specify SKUs, and often it will be there in our mind that, oh, whether it is going to contain, like, consume the output delay. No, it won't. So you can use clocking block, and you can drive the interface signals defined within the clocking block. Any clocking block signal drive doesn't consume any time. And then you can do fork join none, because this is the construct we will see sometime later. This fork will launch multiple threads, and it won't wait. The parent of the fork join none will not have to wait for the threads to complete. It will continue its execution, and hence fork join none construct can be used within the function. So since these do not consume any time, all of these can be used in the function. This is something that you want to pay attention to. It could be a tricky, it could come in as a part of a trick question. So let's look at the subroutine arguments. So when we say subroutine arguments, the scope to understand is, one is automatic versus static, I think, which we have already covered. The second point is bound by position or bound by name during the call. So this is something that we will look at it. And then we have pass by value or pass by reference. So how this works, we will look at it. And then default data type and direction, we have already looked at it. The default data type is logic and direction is input. And then the value part, we have not looked at this this aspect. So we look at the how to pass a default value. So when you understand these four dimensions, you understand what it, I mean, like everything about the subroutine arguments. Not, of course, not everything, but yeah, so these are the key things. Of course, there are always variations, as we have discussed. Everything with respect to programming language, there are core concepts, and then there are exceptions, there are flavors. So those are anyway endless, but these are the core dimensions. So let's look at it, look at the look at each one of them. So let's look at pass by value. So default mechanism for passing arguments to subroutines is via, pass by value. This is the default argument, and the way pass by value works is that it copies each of the argument into the subroutine area, and if the arguments are changed within the subroutine, the change will not be visible outside the subroutine. And when the arguments are large, okay, large meaning, like if I have a huge array, then it can be undesirable to copy the arguments. So the way to understand this is, like, if I am calling this my task, and let's say we have these input variables A, B, and then we have inout variable C, and then we have output D and E. On a task call, what happens is the value of the V and W and X gets copied over to this A, B, and C. So that's what it is demonstrating. And on the completion, whatever the variables that I have passed over here, the argument, the copies from the argument gets the values from the present as the output argument within the function gets copied over to the corresponding variable. So this is the pass by value. Okay, so as you can see, we have two different set of variables, and the values are passed between those two set of variables. So that is what happens when you do the when you pass the argument by value. And this is an example where it is showing, okay, if you have a byte packet 1000:1, then you are passing so many bytes, and this way it gets copied, a copy of this is made, so unnecessarily the memory gets consumed. So this is something that this is something that can be optimized using the pass by reference. So as we saw, the default way of passing arguments to the subroutines is pass by value, but we have the another mechanism where we can pass the arguments by reference. So when you pass the arguments by reference, the variables that you are passing, the values, they don't get copied into subroutine area. Instead, the reference to that original argument or the variable that you are passing gets shared with the subroutine. So it's like you have this common variable, the caller has, let's say, allocated a common variable. The reference to that is the same shared area. Both the subroutine as well as the caller will work together, right? It's not a different area that is created. And of course, the arguments passed by reference have to be matched with the equivalent data types of the formal arguments that you have defined. No casting is permitted. both the caller and the subroutine share the same changes made to the argument within either the caller or the subroutine, right, shall be visible to each other. So if a subroutine changes the values, of course for the function it's not it happens in zero time. So you call the function, it changes and it becomes available to the caller immediately. But in a task, if the multiple modifications are going on, and sometimes if you don't want those modifications to be visible to the external world, but you have to take care that when you pass it with ref, they will be visible. Okay. Of course, when we are passing it with ref, for the function as well, whatever the changes that the function makes will become available to the caller. So the way you do this is like you use this ref keyword, and this, when you use the ref keyword, you cannot again additionally specify the direction. So a ref argument is very similar to inout, except for the fact that, as we saw in the previous slide, so when you use the inout, those arguments, the value gets copied as an input when the task or a function call is made, and as an output when they exit, right? So that is the difference. Whereas the intermediate value changes wouldn't be reflecting, but when you do it as a ref, um, the intermediate values get reflect, and it uses the common storage as well. So to protect the argument, so sometimes what happens is that not every time you are passing the value such that you can work on a common storage. Sometimes you are passing the argument by ref because the task or function is just doing a read-only access, and you don't want to and if it is a big array, you don't want it to be reallocated by the task or function. So you are passing it by reference, not because you want that particular subroutine to make change, but you want it to use the same copy. So that is why you are passing it by ref. So to prevent any inadvertent changes to such copies, you can use the const qualifier. So let's say we saw one function in the previous slide where we were passing the byte packet by value. So if you just add ref keyword to it, then the copy would not be passed. The actual the same the reference to the, or the pointer to the same variable will be passed even to the function, and hence this function will run much lighter in terms of its memory footprint. And the second task, it's showing that okay, it's receiving some dynamic byte array, and that we are passing it with the ref, and we are providing this const qualifier. And when we provide the const qualifier, if we try to change the data, because since the task has the access to the same common storage, if it tries to change it over here, then it will flag error, the simulator will flag error. So you cannot change it, but you can use it only for the read-only purpose. But your overall memory footprint gets minimized. But in some cases, of course, you can change it as well. So you can pass a common reference, and then it can do the changes, and then the subsequent like I could have series of tasks, each one of them doing changes and transforming data in certain way. That model is also possible when you use the pass by reference. So in this slide, we'll look at two things. One is how the default value we can define for the formal arguments of tasks and functions. And second thing is also how do we call by name and by position, like how do we pass the arguments to the tasks and functions by name and by position. So both of those, so all three concepts will look at it over here. So in the subroutine is called arguments with the default can be omitted from call. So what that means is, like here I have defined a task. I am saying int is the arguments, that the formal arguments to a task I am defining. I am saying int j equal to 0. Okay. So any argument where you say that argument name equal to some value, that will be the default value. Now how that default value gets used, we'll find it out in a moment. And then I'm defining a second argument. It doesn't have any default value. And then I have defined another third argument that has a default value of 1. Okay. And So let's understand that so here, so one more factor is that the compiler shall insert the corresponding values when you call. Okay, so like for example, I call this task read and I am saying comma 5. So I'm not passing the first argument, and this is something, this way of calling the task is called call by position. So I am passing the argument by position. So this is the second position, right? So I'm passing the value of k. So this is equivalent to, so the compiler will, here the compiler will insert this value 0, and then I'm passing the value 5, and then the compiler will insert this value 1 because I have provided these default values. So similarly, I can pass argument value to the variable where I have defined the default value, in which case it gets overridden. So now I will be passing the actual value as 2, and to the whichever variable that I have not passed the value, that will get the compiler will insert the default value that I have defined. And so here I am not passing both of them, so it's getting inserted with the default values. And I think we have few more flavors, so I can pass all the arguments as well. So it doesn't mean that if I define the default value, I cannot pass that, cannot pass a different value. It doesn't mean that. So I can still pass whatever the values that I want to pass. When I don't want to pass any values, then the default value comes into play. And here, if I don't pass any arguments at all, then it's an error, because for the int k, since I have not defined a default value argument, it's mandatory that I have to send the value for this particular argument. Since I'm not doing that, it's giving me error. And even if I pass these two and ignore the middle one by position, I will still get a error because I'm not passing the default value. And this default value that I have shown over here in this example are constants, but they can be expressions as well. And if they are expressions, then every time the subroutine gets called, the expression will get evaluated. Okay, and then those values will be made available as a default values. So let's take, like for example, for a function, this way of doing, like the position based argument and name based argument is applicable for both the tasks and functions. So here I have a function int, the return type is int, and then the name of the function is fun. Then I'm saying int j equal to 1. So the default value of argument is 1, and string s is equal to is also has a default value of argument no. So there's no fun. Okay, so we call this function fun, and then here I am passing it through the the named argument. So the way you pass it with the named argument is you use the parameter, the default argument name that you have specified. You say dot and the argument name, and in the parenthesis you pass the corresponding value, and you can say dot s and then pass the corresponding value. So by position it would have looked like this. I would have said fun to s, right? So that's how it would have looked from the position point of view. So in the position, what has to happen is this: the way you pass the arguments, the positions have to match the order in which the function declaration or the function prototype has been declared. But when you pass it by name, you don't really need to preserve the order. So here I can say dot yes, for this particular argument I can pass the value first and then pass the dot j, right? Both of these, the one on the line 522 and the one on the line 518, both are okay when you do the named argument. And in fact you can pass only one argument as well. So as long as if they have the default values, then whatever you want to pass, you can only take that particular argument name and pass the value. But when we did the same via positions, we still have to use the commas. Okay, so the commas still have to match the total number of arguments that you are passing, whereas when you pass it by name, that restriction won't be there. So you can define only the corresponding names and pass the corresponding argument values. And here in the last one we are not even passing any argument because both of them have the default values. So I think, like wherever you can define the default argument values, you should do that. It saves effort in terms of calling the function. It makes it easy for the user. that when he doesn't know if it can work by default. Like for example, I am passing some arguments via command line, let's say some count of transactions that I'm passing via command line. Of course, that's not directly in the context of the default value of task that we are talking about, but in general the concept of having the default values is what I'm referring to. So wherever you know that there can be some default value that can be used when user is not specifying something, it's always good idea to do that. Like I'm passing a count of transactions to be generated from the command line, and if the user is not passing it, you set up some default reasonable value so that even if the user forgets to send it, then test can still do something meaningful. So that I think is a important idea to keep it in mind. So let's look at parameterized tasks and functions. The way, just a quick refresher about parameterization. So what happens is when you have to implement certain common functionality, like let's say if I want to add two numbers of two different data types, let's say I want to add integer and then long integer, and let's say even I want to add two real numbers. See, the internal functionality will remain same. I'll implement a function add, but the data return type of that particular function has to be int, right? Or it could be int, or it could be long int, or it could be real. And the input parameters that I am passing again can be of the type long int, or real. And let's say that the similar type of a functionality I want to implement for different width of vectors, then I need to have the way to customize the width. But what I'm going to do inside that function, I'm still going to add those two numbers and return the result. So that skeleton part remains the same. It's just the data types that are different. So when you have such a type of a problem, right, you have to rely on using the parameterization. So whenever you have different array sizes here, and or the data types or the variable widths, then the parameterization is the way to accomplish way to solve those problems. So here, for example, what we are doing, we are defining some encoder decoder class, and we are passing the parameter decoder underscore w, and then we have another parameter called encoder underscore w. We have the clog2 function which tells you, for example, if I pass a 7 as a value to decoder w function, it will tell me that 3 bits are required. So that's the essence of it. It's a logarithmic function. Now all the parameterized functions have to be of the type static, and they have to be implemented in the virtual class. So that's something that you want to pay attention, that we can't create an object instance of this class, so that's not possible. So we are implementing this static function, but if you see here logic, and then whatever the parameter that we have defined, we can use this. Okay, and then I am passing even, so this is the return type. I am able to use the parameter value, and even for the input parameters that I am passing to the function, I am able to use the parameter value over here. And the way I would invoke it is, I will say encoder out equal to c, and then any parameterized class will have this pound sign. So I'll say pound, and I'll pass the value of parameter. I have to pass only one parameter because encoder w automatically gets derived, calculated in fact based on the value of this decode w value. So I'm passing this particular value 8 over here, and then I am saying encoder of f, and then I'm passing encoder in. Okay, and then this particular guy will now take care for the width of 8, and then this guy will take care for the width of the 4. So I don't have to keep on repeating the same functionality again and again for 8 and 4. If I had hard coded the value of 8 over here, then I had to repeat the same class and implement the same type of a functionality on a different data type. And because of the parameterization, I don't have to do that. And second, so this is one example where we saw the parameterization in terms of the width, but we can also do parameterization in terms of type. Okay, so here we are creating another class, and we are saying type t equal to int, and then again we have a static class, static function over here. And if you see this, we are using the type. So whatever the type, so type meaning I can pass a data type. Typically a class a data type would be passed over here, and then I'm calling that as a transfer, and then this T and then the scope resolution operator, type D scope resolution operator create is a way you create the object instances in UVM, for example, right? So this is the some UVM base class extended class data type that we are passing. So I could be passing here, when I create this particular guy, I am passing AXI transfer underscore T, and the AXI transfer underscore T itself could be extended from some UVM sequence item, for example. So I am passing a class data type over here, and for that type of a class data type, this whole functionality is getting parameterized, and it's able to create an object of the class data type that I'm passing. So this way parameterization is a very powerful feature, and yeah, it's used in the some of the advanced test benches, and all the UVM base class libraries that we are going to see in future, they internally rely a lot on using the parameterized classes, and hence inside those parameterized classes they will use the parameterized functions, and the parameterized functions helps us write like a generic functionality, and that generic functionality we can customize it for these different variations. Okay, so this session we will do the assignment statements refresher. So if we look at the first, let's understand the overall scope. So if we look at it, so assignment, we have two types of assignments. We have a continuous assignments that's typically used for your RTL design for modeling the combinational logic, and then we have the procedural assignments that you do it typically in your initial block or in your tasks functions. So that's where you do the procedural assignments, and procedural assignments are again of three different types. So we have a blocking procedural assignment, which is what we regularly use. This is the even in any programming language you use the blocking assignments. In the blocking assignments, essentially the subsequent statement will be able to see the update that's made in the previous statement for any of the variables. And then we have seen the non-blocking assignment statements, where the whatever the value that we assign from the RHS to LHS actually gets scheduled, and then eventually it gets executed. So this assignment executes in two steps, non-blocking executes in two steps, whereas blocking executes in single step. So in the non-blocking, any assignments that you make, the value would not be visible, so hence it provides that pipeline behavior. So we will see a bit more details about it as we go further. And then we have a continuous assignment flavor, which we can execute in the context of procedural assignment. So what happens over here is, so when we use this continuous assignment statement, this which is outside of your initial or always type of a block, which exists independently, you don't have the control as to when it starts. So as soon as the simulation starts off, this will become active, and whenever the right hand side variables change, it will keep executing again and again. So you don't have the control as to when should it start and when should it stop. Whereas when you do the continuous assignment statements in the context of procedural assignments, so you have something called assign and deassign. So these and force and release, so these type of continuous assignment statements can be enabled and disabled. So at some point in your procedural code execution, you can start off this assign, and then the continuous, then it behaves like your regular continuous assignment statement. That's whenever the values change, it will cause the left hand side to get updated, but then you can do again deassign. At some point of time you can stop it, and the same is with the force and release. So we will look into it more details, but this is the big picture that we need to understand in the context of the assignment statements. Okay, so let's look at the continuous assignment statements. So the expression on the right hand side that we have for a continuous assignment statement, it can be thought of as a combinational circuit, right, that drives the net or variable continuously. So this, I think, as we discussed in the design, it's used for modeling the combinational circuit. And in contrast, when you look at the procedural assignment statements, they just store the values in the variables, right? Whereas these guys, continuous assignment statement drives the wires or the variables, but they just store the values, and then a next assignment will change the values. But whereas in the continuous assignment statements, the way this behaves differently is that once a continuous assignment statement has executed, like let's say this assign has executed, thereon it's not just sampling the values of these variables and storing it in this particular right hand side net. That's not what it is happening. In case of variable, that's what happens when a variable assignment statement executes in the context of procedural assignments. It's just the values of the variables used on the right hand side are sampled, the expression is evaluated, and the value just gets stored. But whereas when a continuous assignment statement gets executed, then based on the values of these variables continuously, as and when they change, the expression gets re-evaluated and the updated value gets driven onto this net. So it's happening all the time. So that is the main difference. And then the assignment, as we said, it occurs to the right hand side whenever it changes. There are two forms of continuous assignment statements. So there's one called net declaration assignments and another is a continuous assign statement. So what the net declaration assignment means is that if I say wire data type, and which is of the net type, if I say wire w equal to variable a and variable b, this by default creates a continuous assignment statement here. So this is the net declaration assignment. So there's one for, and another is I can actually create a continuous assign statement by calling explicitly assign equal to something. So here at the top you can do a wire declaration, and because of the wire, when you do this initialization, it implicitly becomes a continuous assignment statements, or you can use the assign keyword and still initiate a continuous assignment statement. And as we saw, the continuous assignment statement can be done on both the variable as well as on the net data type. When you do it on the net data type, you can have multiple continuous assignment statements working on the particular net, because it will anyway have a resolution function through which it will take care. But when you do it on the variable, you have to make sure that it's only the one driver that's driving the left hand side of the left hand side variable is driven by only one continuous assignment statement. It cannot be multiple. Now if I contrast that with the variable, now the logic is variable. So here this initialization on this line 498 happens only once. So this is very important point that you have to notice, that when you do a wire declaration, it becomes a continuous assignment statements, and whenever the variable a or a variable b changes, the value gets updated onto this target w wire. But whereas when I am declaring a variable, right, so when I declare a variable and I say variable v equal to const a and b, then depending on the value of these right hand side variables or whatever that I'm using gets evaluated only once, the value gets stored. But eventually if they change again, unless and until you call another time assignment statement, the value of the v will not change. So that's the main difference that you might want to take a note. So along with the continuous assignment statement, so we were able to see that we have the left hand side net or variable, and then we have the right hand side expression that gets evaluated. But while we are assigning, we can also specify the strength. The drive strength value can be specified, and the drive strength value specification consists of two strength definitions. So that is, when the value of 1 is driven onto the net, what is the strength that should be used, and when the value of 0 is driven onto the net, what strength should be used can be specified. And if the drive strength is not specified, it defaults to strong 1 and strong 0. So we have other drive strengths that can be used. We have supply 1, supply 0, strong 1, strong 0. We have pull 1, pull 0, weak 1, weak 0, and then we have high impedance 1 and 0. And when multiple drivers are present, so we have been seeing that there will be a resolution function, and the resolution function will depend on two things. One is what is the value that is being driven, and then with what strength it is being driven. So depending on those two, the final value gets resolved. In my experience, I have seen a very limited usage of the strength modeling, and typically it becomes useful when you are doing like a shared bus type of an implementation. So like for example, USB 2 is a shared bus. So when you do the USB 2, then you have the multiple drivers, they are using the same pins. So there's like a half duplex communication. So it's using the same physical wires, and it does the half duplex. So one guy will transmit for a while and then it will stop, and another guy will transmit on the same line. So in those cases you essentially have multiple drivers, and to simulate the effects of those multiple drivers at the physical level, you rely on the different strengths. So and then you sort of model certain aspect of that particular bus using these different strength values, so that if the contention happens, that is, the protocol ensures that both should not drive at the same time, but if at all they do, then these can be used. Or like one type of signaling can override another type of signaling. So that will be the protocol requirement, and the protocol will not say you have to use like either supply or strong, but the supply, strong, pull, weak, these are the elements that you utilize to model it. For example, you want the like let's say weak type of a signaling, because your protocol requires that when a reset is sent, whatever the data that part that you are signaling should be get overridden, then the data signaling you could be doing it with weak. Whereas when the reset is sent from the other side, you can model it with strong, so that the reset value prevails, and then that can be utilized. So this way, for modeling certain aspects, the drive strength values are useful. Okay, we looked at the continuous assignment. So now let's look at the procedural assignment statement. So like the continuous assignment statement can occur anywhere inside the module. They don't need your always initial type of a block. They can occur independently, whereas the procedural assignments occur within the procedures, such as they have to occur in the always, initial, or a task and a function. And as we have discussed a bit about it, that the procedural because the assignment gets triggered when the simulation reaches that particular assignment statement, right? Unlike the continuous assignment statement, wherein whenever any of the variables on the RHS changes, it gets reevaluated and the value gets updated to the LHS. So unlike that, the procedural statements execute only when when the execution reaches that particular point. And once it is done, they store the value, and then it changes only when the next assignment takes place. And once you have done the procedural assignment, even if the values of the variables that you had assigned are changing, will not have any effect on the target variable to which we had done the procedural assignment. That's the main difference that you have to remember. Then you can use event control, like the @named event, or a delay controls, where we can use hash delay some particular value. Then you have if statements, case statements, the procedural statements that we have already seen, and the looping statements, that you can utilize that to figure out whether the assignment gets evaluated or not. So you can use the procedural assignment procedure statements to control whether the flow reaches the assignment statement, or how many times it reaches the assignment statements, and hence whether it gets executed, or some cases whether it gets executed or not. So we have seen that the procedural assignment statements are of three types, right? We have blocking, non-blocking, and continuous assignment executing in the procedural context. So let's look at the procedural blocking statement. Blocking procedural assignment statement, the basic idea is it should execute before the execution of the statement that follows it in the sequential block. Okay, so that the effect of it can be seen by the next statement. That's the main idea. And we have already looked at some of these operators, the simple, equal to, plus equal to, minus equal to. So these operators that we have already looked at in the context of operators. Now all of these are blocking assignment statements, and the syntax of it will be that you have the value variable on the left hand side is equal to some delay or event control followed by a expression, and the delay or event control is an optional intra assignment timing control, right? So this, the value of assignment from the right hand side to left hand side occurrence, you can control it with the help of this delay or event control. So what happens is, if you have some expression, like for example if I have a and b, so the expression gets evaluated immediately. Okay, so if I have put some delay over here, the expression a and b will be evaluated based on the time when this particular blocking assignment takes place, but the value would not be assigned to the left hand side immediately. So what happens is, so this, like for example if I have register equal to some hash delay and expression, if this is my procedural blocking assignment statement, then the equivalent of it is that I will have one temporary variable, so the expression gets evaluated immediately before the delay, and that expression gets assigned to this temporary variable, and then after the delay, right, after the delay, then the value that I had stored in the temporary gets assigned back to the register. So this is how the intra assignment delay takes effect. Okay, so the second category we have is the non-blocking assignments. So the non-blocking assignment allows the scheduling of assignment without blocking the procedural flow, and they are typically used when you want to assign several variables, and you are looking at an effect that all of them are getting assigned in parallel. Essentially, that is the effect that you are looking for, and even when you do it in the same time step, because they are all happening parallel, there won't be like the dependence of the interdependence between the assignment order will not be there. Like for example, let's look at this classic example. So here in this initial block, I am saying a is equal to 0 and b is equal to 1, and I am saying at always at passage of clock, I am saying A with non-blocking assignment of B and B with the non-blocking assignment of A. And here what happens is that the non-blocking assignment, as we know through the scheduling semantics as well, that it executes in two steps, right? So in the active region, it gets evaluated and it samples the value of B and A, but the assignment won't take place. So the B value will be 1, that will get sampled, and the A value will be is equal to 0, that will be sampled, and that will be the event for assignment will be created. But the assignment itself to the left hand side variable will not take place. When in the same time tick, when you reach the non-blocking assignment, then you actually assign the value. So when you assign the values, then we had already sampled the value of B as 1 in the active region, that gets assigned to A, and then A's value that we had sampled, which was equal to 0, gets assigned to B. And if this whole statement was of a blocking type, then what would have happened is I would have said A equal to B, which would have meant that the value of B, which was equal to 1, would have gotten transferred to A, and then when I had said B equal to A, the value of A would have been visible. Okay, so it would have come to 1, so both of the variables would have ended up with the same value, whereas if I am using a non-blocking assignment, then both the variables will get a different value. So the non-blocking assignment compared to blocking assignment, it takes place in two steps, and that's how it creates the sort of the pipeline effect that we had seen in the context of, even in the context of the clocking block we had seen, and we had seen it in the context of how it helps to avoid the race in the context of our scheduling semantics. So let's compare the procedural non-blocking versus blocking, and with the intra-assignment delays, and see how the behavior is. So I have these 6 variables, and then I have 2 initial blocks, and then I am in the first initial block, I am doing the blocking assignments with some intra assignment delays, and in the second one I am doing blocking assignments with the non-blocking. I'm doing non-blocking assignments with the intra-assignment delays. So in the first one, when I do a equal to hash 10 of 1, the a will be assigned 1 at the time of 10. But because the blocking assignment is blocking in nature, the control won't go to this assignment unless and until this one completes. So at time 10, the b equal to hash 2 of 0 will be executed, and hence b will be assigned to 0 only at the time of 12. Okay, so it has to wait for this 10 plus 2, and then the delay becomes additive, right? Then the c will be assigned to a value of 1 at the 16, because it has to be this 10 plus 2 plus 4, it has to wait for that. Whereas when you do the non-blocking assignments, all of them in essence execute parallel, because when this statement gets executed and it gets scheduled to be assigned at 10, at the same time this e equal to gets executed, and then it gets scheduled to be assigned at 2, and this gets executed. So all of them execute at the same time step, but the scheduling of the assignment of the value to the RHS from RHS to the LHS assignments get scheduled at the different points of time. So D will get assigned at the value of 10, and then E will get assigned at the value of 2, whereas here it was 12, right? So here it is 2, because the effect of this assignment is not seen for the next assignment statement, and hence they are executing parallelly. So that is the effect that the non-blocking assignment will create. Okay, so let's look at few more examples of the non-blocking statement. So in this initial block, for the same variable, we are assigning different values with the same intra-assignment delay. So in such scenarios, what happens is both of them get scheduled, and since they are executing in the same block, the order will be respected, and hence the value of the a at the time 4 will be equal to 1. So this order gets preserved in such cases. Although it's non-blocking, the order gets preserved. And here we have a for loop. So I'm saying for I equal to 0 to less than or equal to 5, and we are assigning the values to a common variable r1, and this loop will complete execution in 0 time. It won't consume any delays. Okay, because we are doing the non-blocking assignments, all of them will complete in 0 time, but the actual value assignments will take place at different points of time. When the loop index it executes with a value of 0, this will be with a 0 delay, and I of 0 will be 0 at that point of time, and so we will see the 0 being assigned to the R1, and then at the point when the I becomes 1, this will become 10, and the I of 0 will be value of 1 at that point of time, because the index value is 1, and hence that is scheduled at the value of 10. The 1 is scheduled, and similarly at the when the index becomes equal to 2, it will become 20, and at that point I of 0 will be 0, and hence at 20 the 0 is scheduled. So all of these 6 assignments, right, so they get executed at the point when this loop executes within the 0 time, but the actual assignment will take place at different points in time, depending on the intra assignment delay that we have specified in this non-blocking assignment statement, and hence it will end up producing a waveform like this. So these are sort of various forms of how the non-blocking assignment manifests, but the bottom line concept is that a non-blocking assignment will execute in 2 steps. In the active region, the evaluation will take place, and in the non-blocking assignment region, the actual assignment will take place. So that concept, if it is clear, then you can repeatedly apply to different scenarios. Okay, so we have looked at the 2 forms of procedural assignment statements, the blocking and non-blocking. Now we'll look at the procedural continuous assignment statements, which are assign and deassign. So as we had discussed at the beginning of this assignment session, so the main value that this assign and deassign statement brings in is it provides the timing control for the activation and deactivation of your continuous assignment statement. That's the main value that this particular construct is bringing in. And let's take a look at one example and to understand it further. So we say assign some register variable is equal to some expression 1, and here this continuous assignment statement, procedural continuous assignment statement, also called as a quasi continuous, takes effect. Okay, so once this takes effect, then any changes in the expression 1 will be evaluated and updated to register all the time. Now if I do a procedural assignment like register equal to expression 2, it will not have any effect, because this particular assignment is happening continuously. So this one instant moment, if I try to do this assignment, the storage type of an assignment, it will have no effect. But if I do another continuous assignment statement with a different expression, then this particular expression becomes active, right? And it overrides whatever that previous assign that I had made. Now if there is any change in the expression 3, then that will take effect on your left hand side, and then maybe you do some more logic processing, and then you say deassign this particular register, then the procedural continuous assignment statement gets deactivated, and then thereon if I do any more assignment, procedural assignments. So when I say procedural assignment, the expression 4 gets evaluated and the value gets assigned to register 4, but thereon if at all the expression 4 changes, it will not have any effect on your the value of register. Now here in the overall scheme of things, you observe two things: that you are able to control the time at which this particular assign takes effect. And then when you want the continuous assignment statement to stop, something like this, if you have to do it through the you cannot, do it directly through the continuous assignment statement, the regular continuous assignment statement. So this is the benefit that the continuous assignment statement used in the procedural context provides, and it will override all other procedural assignments to variable, as we saw over here. And the deassign state procedural assignment statement will end the procedural continuous assignment to variable, freeing it up to the regular procedural assignment. So that also we have seen. Of course, it as we discussed, it allows the timing control. Okay, so we have looked at the procedural continuous assignment statement made up of assign and deassign. So in this one, we'll look at the force and release. So the effect of the force and release is similar to our assign and deassign pair, but force can be applied on nets as well as variables, where the assign and deassign was only for the variables, but the force we can do it on net as well as variable. So that way it's sort of a superset. Force a statement to variable, if you do, it will override your if there is any procedural assignments, the regular procedural assignment will get overridden, and even if there is any continuous assignment that is taking place as a part of design logic, that will get overridden. And any assigned procedural continuous assignments, if they are active, they will also get overridden until the release statement is executed. Like similar to assign and deassign that we saw in the previous slide, the force and release, unless the release is executed, the force will stay in effect. And similarly, the force can be applied on net as well, and it will override all the drivers. Okay, and like that could be like either an output of a gate or a module output, or any continuous assignment that is present within the design that will get overridden until the release procedural statement is executed. And similar to our assign and deassign, they will execute in the procedural context, meaning in some begin and end, when the statements are executing one after another, you will be able to execute force and release as well, right? And when released, the net shall immediately be assigned with the whatever the value that is determined by the active drivers on that particular net. Now as far as the use cases of force and release are concerned, so often we have X propagation in gate level simulation. So what happens, you do the RTL and the RTL gets synthesized to gate forms, and the simulation are performed even on those gates netlist to check that whether everything is doing correctly. And what happens is, in some cases, just to save on some area, some of the flops in the RTL could be may not be having the asynchronous resets, because it doesn't matter. But what so those in the RTL simulation behave okay, but in the gate level simulations, those uninitialized flop could lead to X propagation. X is the unknown value, so they will have the output of unknown, right? Because they do not have any reset, so they will have unknown output, and that unknown will propagate and cause failures. Okay, and those, many of the times, those failures could be just a false failures. Okay, so now to overcome those false failures, what we do is we force those flop outputs to some initial value using the force statements from the test bench. That's what we do in the gate level simulation. So that's one area where predominantly the force and release are utilized. And the second area, so those registers eventually get initialized by the test. So till they get initialized, you sort of force them, and once they get initialized, you release them. And the force, in fact, itself has certain variants where you force till the value gets updated. So using those variants, you can do the force. And we can also use the force and release even during the RTL simulation sometime. Like for example, as we had seen in our 256-bit counter verification with Verilog, the rollover was a problem, right? So we had invented the enable mechanism to preload the count, and then we used it to cause the overflow, or the rollover. But what we can also do is we can use force statement. In fact, this is one experiment that you guys should perform, that you force the counter output to a value much closer to your rollover value with a argument to the force such that it only deposits the value, and then when the next clock, when the change in the count takes place, that change itself will bring in a new value, and it will lead to eventually the rollover of the counter, right? So that experiment you guys can perform. And so in some cases where it takes longer simulation times to reach a certain state, you can use the force to get to that state, and eventually release it to when that particular effect has been seen, to verify certain parts of the logic. Okay, so we have closed on the first part of the procedural programming. We have been able to close the procedural programming statements, which included our if and then loops, case statements, jump statements. Then we have covered tasks and functions, and like the concepts of automatic and the static variations of it, and then how do you pass arguments, how does the pass by value works, how does the pass by reference works. So some of the key concepts covered in the context of tasks and functions. And we have also covered assignments. We have in fact refreshed it. We have looked at the different types of assignments that are supported. We have blocking, non-blocking, in the form of the procedural assignment statement. We have a continuous assignment statements, and the timing of the continuous assignment statements can be controlled using the procedural continuous assignment statement. So we have closed on all those. The next part, we will look at the process and the interprocess communication. That's a key topic. Is a very important part of the overall, both as well as Verilog as well as from SystemVerilog point of view. So we will look at that in the next session, and thank you for listening.